Welcome everyone. In this video we are going to build a pulse chain signal generator, a complete istable multivibrator on a breadboard using BC812 PNP BJT transistor. We will go through the full theory and verify our output on an oscilloscope. So let's begin. So first of all, what is a multivibrator? A multivibrator is a two-stage switching circuit. There are three types of multivibrator: monostable, bistable and astable. So in an astable multivibrator, there is no stable state. That means the output of the circuit continuously changes between two states, and the duration for which the output remains in one particular state can be controlled by the passive elements like resistors and capacitors. So this is the circuit of our pulse chain signal generator. It is built using two transistors. This is a first transistor and its corresponding base and collector resistor, and this is our second transistor, is corresponding collector and base resistor. We are using two capacitors here, and to understand the full theory, we have to know how BJT transistor acts as a switch. When the base emitter potential is less than 0.7 volt, it will operate in cutoff region and acts as a open circuit. And when the base emitter voltage is greater than 0.7 volt, it will operate in saturation region and acts as a short circuit. Now let's understand the theory behind this. Okay, let's forget about the capacitor for the moment. At the beginning, when there is no supply voltage, both the transistors are in cutoff region and they act as an open circuit. For this, when we apply the supply voltage, the voltages of both collector terminals became equal to the supply voltage VCC, and the voltage of base terminals began to increase through R2 and R3. At that moment, when the both base terminals get 0.7 volt, the transistor acts as a short circuit and current starts to flow through the collector and the emitter of the both transistors. So how does the change happen in the output? For the change in our output, we need capacitors. So let's start from the very beginning again. When there is no supply voltage, both the transistors are in cutoff region or simply open circuit. As soon as we apply the supply voltage, the voltage of both collector terminals became equal to the supply voltage VCC. As the positive side of both the capacitors are connected to the collector terminals of the BJTs, they also get the supply voltage VCC, and the base terminals of both transistors will begin to increase up to 0.7 volt through R2 and R3. As the positive side of the capacitor are connected to the collector terminals of the transistor, they will begin to decrease, and the base terminals of the transistors are connected to R2 and R3. They are going to increase up to 0.7 volt. At that moment, when the voltage of the collector terminals will become 0 and the base terminals with 0.7 volt, both the transistor will be in the saturation region and acts as an short circuit. As the transistors are in the saturation region, the voltage of the collector will be equal to the voltage of the emitter, that is 0, but the capacitor has to maintain its previous voltage difference between two sides for the some time. For this thing, that the gradually increasing voltage of this terminal is 1 volt, and the voltage of the terminal of these terminals is 0.7 volt. So the difference is now 0.3 volt. But now so here the voltage difference is 0.3 volt. But now when the transistor is in saturation region, here the voltage is 0 volt. So here voltage will be minus 0.3 volt. Now, even though the transistor Q1 and Q2 are on the run to operate in saturation region, both cannot be saturated at the same time. One will be saturated first. So we will assume that Q1 be saturated first. That means the voltage of the collector terminal will be equal to the voltage of the base terminal, that is 0 volt. That means the positive side of the capacitor C1 will be 0 volt and the negative side of the capacitor C1 will be minus 0.3 volt. As the negative side of the capacitor C1 is connected to the base voltage of Q2 transistor, so the Q2 transistor will be in cutoff region. So we will got our output to here, that will be equal to our input voltage VCC. So now our Q1 transistor is in saturation period. The positive side of the capacitor C1 is constant at 0 volt and the negative side is discharging through R2. And for the capacitor C2, the negative side is constant at 0.7 volt as it is connected to the base voltage of Q1 and the positive side is charging through R4. So the collector voltage of the Q2 is decreasing. So when Q2 will be in saturation region, the voltage here will be 0 volt. So some minus voltage will come here. That's why our Q1 will be in cutoff region, and we will got our output here that will be equal to our input voltage VCC, and that happens over again and again.
So this is our circuit which is generating positive signal generator. We have built our circuit according to our theory. For input we have connected 10 volt DC here, and we are taking our outputs from the collector terminals both of our BJT transistors. Now to observe the output clearly, we will connect the oscilloscope channels to our circuit step by step. First, we take channel 1 of the oscilloscope. The positive probe of channel 1 is connected to the collector terminals of the first BJT transistor because this is the point when we want to measure the output signal. Then we will connect the reference or the ground clip of the oscilloscope to the common ground of the circuit. Next, we will connect channel 2 of the oscilloscope to the second BJT transistor. The positive probe of channel 2 is connected to the collector of the second BJT, as this is the point we want to observe the second output signal. The negative or the ground clip of the channel 2 is left unconnected because in most of the oscilloscope, the ground terminals of channel 1 and channel 2 is internally connected or shorted. After connecting the input voltage and the oscilloscope channels, this is our output waveform. Now we will measure the output using the oscilloscope. First, we have applied a 10 volt DC input voltage. Theoretically, we expect to get around 10 volt at the output. Now we will measure the output voltage using the oscilloscope to verify this. Now we are observing the output from the collector terminals of the first BJT transistor, and we can see that the peak-to-peak voltage here is 10 volt, which is equal to the input voltage. Now we will measure the time period of the signal. Now we are going to measure the time period of our output waveform. From theory, we know that the total time period is given by T is equal to ln2 into R2 plus R3 into C1, since our C1 and C2 are identical. In our circuit, we have used R2 and R3 100 kilo ohm and C1 and C2 0.1 microfarad. So the theoretical time period comes out to be approximately 13.7 milliseconds. Here we can observe that our measured time period is about 12.9 milliseconds, which is very close to our theoretical value.